Alright students, the final video on light is about index of refraction. Index of refraction is given by the variable n, and this n is not so much a variable as much as it is a feature of a material. Okay, so let's look first at a table of materials so that you can see the various values that this has for those materials. Okay, so we have our table of values, and let's talk about what these mean. The index of refraction of vacuum is what we mean by that is the index of refraction of space. So there's no air, there's nothing, there's just nothingness, right? That is going to be 1 by definition, so let's remember that. Air is almost the same because, I mean, air, there's not very much to it, right? There's just some molecules flying around, right? Water is a much denser substance, and so it goes up a little bit to 1.33. I don't like all these 3's on here, but ice is a little bit different than water because ice is a little bit different than water. Glass, it depends on the kind of glass, but a lot of the times it's around 1.5. And then diamond is a very specific value. So notice that as we get more dense, we tend to have higher index of refraction. So what does that mean for light? Well, for light, there's a couple of things that occur. So here is the number one thing that we're going to think about, and that is the definition of the index of refraction. The definition of the index of refraction is the speed of light divided by the speed of light in a material. So I told you before that light actually slows down when it goes into materials. So we're going to take a material like a little block of, I don't know, glass, and we're going to send a ray of light through it. And when I say a ray, I don't mean like, I'm not, there are waves involved with our light, like so, but what we're going to do is just look at a ray of light, okay? So I send a ray of light, and I'm going to, oops, I should make that a little bit more like a line, shouldn't I? A ray of light, and when I send it through, I'm going to send it exactly face on into that material. I'm not going to send it at an angle or anything like that. It's going to be exactly perpendicular to the surface of this material, because later we're going to change that. But for right now, we're just going to keep it like this. And then it's going to go into the material, assuming that it's something like glass and not something like a piece of metal or something like that. It's going to go into the glass, and it will have a speed outside of c, but inside it will have a speed whatever that velocity in the material is. The index of refraction is what determines the ratio between the speed outside and the speed inside. Okay? Now, you may be asking, well, what the heck is this word refraction for? We'll go over that later, okay? But for right now, it should just be clear that this index of refraction is very important for determining how light kind of gets sluggish when it gets into materials. Now, using this, we can actually calculate if we have a glass that has an index of refraction of 1.5, like it says in the table, then we can use this fact to find out how fast light is moving in glass. So the velocity of light in that particular glass, what do we need to do? We need to calculate it using this equation. Now this is going to take a little bit of algebra because what we're solving for is the velocity. So the first thing we need to do is we need to get the velocity in the upstairs position and not in the downstairs position. So we need to multiply velocity on both sides. So the first thing we'll do here is multiply velocity of our material times the index of refraction on the left, and then multiply it times c over velocity of material on the right so that we can get them to cancel on that side. The next step is that we're going to divide through by the index of refraction n, so that we can get the velocity by itself, because that's what we're solving for. So we'll get how we want c divided by the index of refraction. So if you work through your algebra on that, you should come to this conclusion. If you have any trouble with that, let me know. And so that is equal to, what is c? C is 3.0 times 10 to the 8 meters per second. And the index of refraction of glass is 1.5. This doesn't have any units because it's given as a ratio of speed per speed. So index of refraction doesn't have any units. I'm just going to leave those units out, and I should get meters per second. And that's going to give me, if we punch it in a calculator, that should give you 2 times 10 to the 8 meters per second, or 200 million meters per second. Okay, so we now know what that velocity is for light in glass. Now you can see that it moves quite significantly slower in diamond, because as the index of refraction goes up, the speed of light goes down in that material. Okay, so that's the first feature of index of refraction. The second one is also pretty cool, but we're not going to go too far into the math of the second feature. We just want to understand the idea behind it. What happens if I don't shine this light into this glass at a straight on into the face, but instead I do it at some angle? Okay, so we have our piece of glass again. We're going to keep on going with that same piece of glass that has an index of refraction of 1.5, and we're going to shine a ray of light into that glass. Now that ray of light is not hitting the face perpendicular. Instead, it's hitting at some angle, and we have to really define what that angle is in order to be able to figure anything out about this. So we always choose the angle of the ray with respect to the perpendicular to the surface. Now remember, we first off had a ray going perpendicular to the surface, and then we moved it from that angle, so that is our reference angle, okay? So always, when you're doing this, always make your reference line. So now that we have this reference line in place, we can draw our angle, and I'll give it that good old angle theta that we've been using this whole time, that Greek letter theta. And now that angle is going to be kind of important. Just like the angle that we used for the law of reflection, this is going to be an important angle for determining where this ray of light is going to go. So our ray of light is not going to continue in a straight line. Instead, at the surface here, it's going to bend. So let's draw our straight line first so we can indicate where it was planning to go before it hit this surface. Okay, so here we've shown what direction that ray was planning to go, and now we're going to show what direction it actually goes. So here's the direction it goes. Why though? So we can look at this and say, okay, well, I have another angle that I'm interested in here. That is the angle of refraction. Okay, it's a whole different angle, and if you notice, this angle is squished and this angle is not. And you'll also notice that we went from air, which was not a very dense material, into glass, which is a more dense material. So you can think about it like this: the ray of light, as it goes into the glass, is actually going to squish in more to this dotted line than the ray out here, because it's in a denser material. So denser material means denser lines here, okay? This is an important behavior for materials because it helps us to actually redirect light and make things like eyeglasses and other forms of lenses. So this redirection of light is also important for another reason, and it's the same idea as what we saw in a mirror, which is that if light leaves a piece of glass, then it is redirected and it goes to a place where your eye is tricked into believing that it came from a different place than it actually came from. Let's take a look at what that means, okay? We're going to look at a fish in the water. Okay, we have our little goldfish in the water, and we're going to look at our goldfish by seeing a ray of light that came from the goldfish. Now, it's important to remember what we said about the apple in the previous video. If light is coming from the goldfish, right, the only way we can see the goldfish is if a ray of light came from the goldfish and went smack into our eye, right? So, if we want to make a ray from the goldfish that's eventually going to get to our eyes, let's take a look at the way that we would maybe expect this to work, and then let's take a look at the way that it actually works. So I've drawn a line of sight from the fish to the person's eyes, but it's important to keep in mind that since rays of light bend whenever they get from the interface of one material to another, that is not the line of that light is going to take to get from the fish to this person's eyes. So instead, we would look at what happens when a ray of light goes from a dense material into a less dense material. And so we're going to draw a line where we expect this to occur. And we'll expect it to be somewhere around here. I don't think that you would know that immediately, but I, from practice, have noticed this. You have to try out several things to be able to figure it out. So what we're going to do is have a ray of light that goes from the goldfish to the surface. So let's take a ray of light just like that. There we are, a little golden ray of light, and when it strikes the surface, it's going to do so at some angle. Notice here that this angle of incidence is upside down from what we looked at before. It is not entering into a material, but rather it's leaving a material. So again, we have to say, well, what's the direction that this thing was going? That's the direction that it was going, but it's going to bend, and which way is it going to bend? Well, if the perpendicular here is at an angle theta from our ray of light, and the dense material, then when it gets into the lighter material, the less dense material, then that angle should get larger, right? Remember, because the angle in the dense material is squished and the angle outside of the dense material is now expanded. So we would expect this thing to not go in the direction along this line and not bend inward toward that dotted line, but instead would bend away from that dotted line because the new angle is going to be larger because it's in a less dense material than the angle that's within the material. So let's draw that line. Now, observing this phenomenon, you have actually seen this effect before when you look at things in the water. This is what makes spearfishing so difficult. Because if you take a look at this, after looking at all this stuff, if we were to forget about this dotted line here, because that thing is not even going to be useful, not at all. This dotted line, that's not where light went. Where light actually went is it came from the fish and it bent at the surface according to the theory of refraction, and we actually saw the fish, but we have to ask now the question, where did we think that we saw the fish? This is where we think we see the fish. So you've seen this effect whenever you look in water or you dip like a pencil. If you want to try it right now, get a glass of water, take a pen or something like that, not a pencil, it's wood, but a pen or something like that, and stick it in the water and it looks like it bends. And the reason is because where it actually is and where it appears to be are in two different places. So this is an important principle. Let's go ahead and summarize what we've done in this video so that you can be absolutely clear about the message. Okay, so the first item that we discussed, the index of refraction is a feature of materials, and that feature determines how quickly light travels on a material, and it also determines how much it bends at the surface. Also, another factor in determining how much the light bends at the surface is the angle that the ray of light strikes the surface. We remember that the angle is tighter for dense materials and the angle is expanded for less dense materials. Now, one of the only equation that we went over was the speed of light equation on part 2 here, and that is given as the definition of the index of refraction is the ratio of the speed of light in a vacuum over the speed of light in whatever that material happens to be. Okay, any questions on this, let me know, and I'd be glad to answer them, and I will see you guys in the online session.